Tastes over leisure are almost certainly not quasi-linear, which implies that we cannot simply use the labor supply curve as if it was the compensated labor supply curve along which we can measure a worker's surplus. In this graph, we'll investigate a special case, a case where the uncompensated market labor supply curve is perfectly inelastic, but where a deadweight loss appears once we look behind what goes on in the picture. We begin with a picture of the labor market, where we have a perfectly inelastic labor supply curve. We know from our previous work that a tax will always be disproportionately passed to the side of the market whose behavior is relatively more price inelastic. Here we have the case where the worker's behavior is perfectly wage inelastic, which means that the entire burden of the tax will be passed to workers. The take-home pay for a worker will therefore fall from the original equilibrium price W star to W star minus T when the tax T on labor is imposed. You can think of this again as a tax wedge equal to the size of the tax on labor being introduced to the left of the original equilibrium point. Only here, since the supply curve is perfectly inelastic, that wedge will lie right on top of the supply curve. If you have trouble seeing this, draw a supply curve that's almost perfectly inelastic, and then see what happens as you straighten it out. In panel A, it sure looks that there is no deadweight loss here, no deadweight loss triangle like the one we had in graph 19.5 panel A. But the fact that there's no triangle here doesn't actually imply that there is no deadweight loss. The reason we could use the triangle in graph 19.5 is that we assume that underlying tastes are quasi-linear, and therefore the demand curves themselves isolated fully the substitution effects that are responsible for deadweight losses on the consumer side. Here, the consumer side is really the worker side because the worker's part of the equilibrium emerges from the consumer model. And to see where the deadweight loss is coming from when worker tastes are not quasi-linear in leisure, we have to go to the consumer picture, where we plot the initial budget constraint at the higher wage W star and the after-tax budget constraint at the lower wage W star minus T. On the after-tax budget constraint, this worker optimizes at bundle A. Since the worker's behavior is perfectly wage inelastic, that means that the optimal bundle on the without tax budget constraint is bundle C. We wouldn't even have to know that bundle C is the optimal before tax bundle to determine the tax payment this worker makes after the tax is imposed. This tax payment is simply the difference between the budget constraints at the leisure level that the worker consumes after the tax is imposed, the difference here between A and C. We first developed this way of representing tax payments in the initial chapters on consumer theory, where we showed that all we really have to know is the after-tax bundle, and then ask, if leisure consumption stayed at exactly the same level, how much in other goods consumption could the worker have engaged in had the tax not been imposed? That is given by C, and so the difference must be what the worker had to pay in taxes when optimizing at A. To determine deadweight loss, we ask how much could we have taken away from this worker without distorting the wage and made him just as happy as he is under the wage tax. In other words, how much could we have shifted the original budget constraint inward without changing its slope and still get to the indifference level UA. This occurs at bundle B, where the movement from A to B is the substitution effect that will ultimately cause the deadweight loss. The vertical difference between the original blue budget constraint and the dashed green budget constraint is the lump sum amount we could have taken away from this worker without making him any worse off than he is under the wage tax. This lump sum amount is indicated here as the distance L. The difference between how much we could have taken and how much we actually got in a tax payment, the difference between L and T, is the net deadweight loss that's caused by the substitution effect in panel B. The difference between a worker's leisure endowment and the amount of leisure he actually consumes is equal to the amount of labor that he supplies to the market. This is indicated here as the distance L star. We can now see what really happens in panel A by using what we learned in panel B to reconstruct a portion of panel A. We begin with the perfectly inelastic labor supply curve, but now make it explicit that this is the uncompensated labor supply curve. We then introduce the compensated labor supply curve that corresponds to the after-tax utility level, UA. Since compensated supply curves only include substitution effects, and the substitution effect unambiguously says that as the wage goes up, this worker will work more, this compensated labor supply curve must be upward sloping, and it must pass through A because it is the compensated labor supply curve that corresponds to the after-tax utility level, UA. The substitution effect that points in the direction of less leisure as wage goes up in panel B therefore points towards more labor as wage goes up in panel C. The tax payment T that is made by workers in panel C is simply the tax T, which is the vertical difference between the two wages, times the amount of labor that's actually being transacted. Thus, the tax payment T is equal to the shaded blue area labeled A. The lump sum tax that we could have taken from this worker without making him any worse off than he is under the tax is the area A plus C. To see this, all we have to realize is that the worker is equally happy at points A and B because they both lie on the compensated labor supply curve for the utility level UA. You can also see in panel B that they both lie on the same indifference curve, UA. If the worker is equally happy at point B as at point A, but is getting a surplus of A plus B plus C at point B, whereas he's only getting a surplus of area B at point A, it must be that he gave up A plus C in the lump sum tax to make him equally happy. The deadweight loss is then equal to the difference between the lump sum payment L and the tax payment T. The lump sum payment L is equivalent to the shaded areas A plus C, whereas the tax payment T is equal to the area A. Thus the deadweight loss is the shaded magenta triangle labeled area C. While workers therefore inelastically supply the amount of labor L star, this inelastic behavior masks offsetting wealth and substitution effects. It is a substitution effect that gives rise to deadweight losses, and therefore the fact that the substitution effect is fully masked means that the market supply curve that's perfectly inelastic is fully masking the deadweight loss that lies underneath. The reason quasi-linearity gets us out of all this is that quasi-linearity eliminates the possibility of income or wealth effects, and thus implies that the market curves only represent substitution effects. Being aware of the potential of wealth effects masking substitution effects that give rise to deadweight losses is then particularly important when those effects are offsetting, as they are likely to be in a labor market. Another market where that is likely to be the case is the capital market, which we'll deal with in graph 19.7.